Hello all esteemed viewers and enthusiasts of ever-evolving world of technology. Welcome to today's video lecture topic on Introduction to Semiconductor and their applications under the course name it's Semiconductor, PN Junction and Digital Electronics Fundamentals. My name is Nisargo Chand, Assistant Professor in the Department of Electronics and Communication Engineering under School of Engineering and Technology at Adams University. I am very much delighted to embark on this journey with you as we explore the fascinating realm of semiconductors and delve into their myriad applications that shape our modern technological landscape. To begin, let's understand the fundamental concept of semiconductors. Semiconductors are materials that possess a unique electrical property, falling somewhere between conductors, that materials that allow easy flow of electrical current, and insulators, that material resist the flow of electrical current. This intermediate conductivity is what makes semiconductors pivotal in the field of electronics. At the heart of semiconductor lies the crystalline structure of materials like silicon, germanium, and gallium arsenide. The arrangement of atoms in these materials allows for precise control of electrical conductivity, a characteristic that forms the basis of countless electronic devices that we use every day. Now, let's start with my presentation. Here you can see that the wellness evolution where the different emerging technologies are there. So as we start with this applications, what the theory behind this? We start with the application of semiconductor materials that in today's world that electronics, especially the embedded, will simply die if we remove semiconductor components from it. The semiconductor has applications in almost every sector of electronics. Let's have a look at a few applications of semiconductors. The first one, consumer goods, that is electronics. We can't think of a world without electronic devices. That's mobile phones, laptops, microwaves, refrigerators. All these applications are using semiconductor components like diode, transistor, MOSFET, integrated chips, etc. Second one is the embedded systems. Embedded systems, that microcontrollers or microprocessors, have revolutionized the world and are considered the base of embedded systems. These embedded controllers have nanotransistors, semiconductor components embedded in them and acting as a like smart watches, any smart gadgets. So semiconductor play an important role in embedded systems as well. Next, the thermal conductivity. A few semiconductors have high thermal conductivity and are thus used as a cooling agent in thermoelectric applications. Next, light emitting diodes. There's a huge application, as we all know, that instead of heat, a few semiconductors also produce light and thus used in the LEDs, OLEDs, etc. These semiconductors are normally available in liquid or amorphous form and are used as a thin coated film. So these are the applications of the semiconductor materials. So starting with that, you at first you have to understand what the theory behind this, what is semiconductor and what are these different devices like diode, transistors. So let's start with why semiconductors. The first one, why semiconductors? So yes, they are here, there and everywhere. That computers, palm pilots, okay, laptops, anything, that intelligent system that built by silicon MOSFETs, ICs, CMOS. Next, cell phones, that pagers, that is silicon ICs, gallium arsenide, FETs, BJTs. CD players, aluminum gallium arsenide, uh, that is indium gallium phosphide, laser diodes, etc. TV remote, satellite dishes, fiber networks, traffic signals, everywhere, as you can see, the different semiconductor materials like elementary, like compound, any materials it's using in nowadays. So what is electronics? Starting with, electronics is the branch of science that deals with the study of flow and control of electrons and the study of their behavior and effects are in vacuums, gases and semiconductors. So electrons are physically exist as we all know, but holes are virtually, because absence of electrons, that means your positive charge carriers. So as you can see here that there is your electron. Yes, I just show the pointer. Yes. So there is your electrons flow, and in the opposite direction there is your current flow, that is called the conventional current. Next, electron flow in a simple circuit is a piece of conductor, as you can see, and when you put biasing into that, the positive and negative, there is your electron flow in one direction, and definitely there is opposite direction in your current flow. So when the amount of charge that passes a point in 1 second is 1 coulomb, the current is 1 ampere. So that is the ideal concept of any piece of copper wire, that how current you can generate. Next, what are the different passive and active devices? The passive devices like resistors, capacitor, inductors, these are mainly passive devices. Few diodes are the passive device, but mainly other diodes and transistors are the active devices. But what is passive device? Passive device means it does not require any external power supply to make it active. And what are the active device? That requiring a source of power to operate. It requires external power supply to make it active. That includes transistors, integrated circuits, LEDs and other diodes and SCRs, etc. Now everything is now based on the integrated circuits or chips. So what is under this integrated circuit? Integrated circuits that built by nothing but the transistors. So all an IC is a collection of electronic component like resistor, transistor, capacitors, and all stuffed into a tiny chip and connected together to achieve a common goal. So there are various chips for the different functions like logic gates, 74 series, IC 74 series, op amps, IC 741, 555 timers, voltage regulators, motor controllers, microcontrollers, everywhere you can use the ICs or chips. Very basic things that we need to discuss, that what is Ohm's law, right? So Ohm's law based on V is equals to IR, that we all know. But if I can say that X axis is voltage and Y axis is current, that means always you can say that current is depending on voltage. Voltage is always in the X axis, current is always in the Y axis. Why? Because voltage is independent, current is dependent. Current is always depending on voltage. So opposite, it's not possible. Like X axis is current and Y axis is voltage, it's not possible. And you can see the basic phenomena of the current, that is inversely proportional to resistance for a constant voltage. As you can see the graph, that at the very first, when resistance is almost zero, the current is in maximum. But when resistance is increasing gradually, then you can see currents are also reducing. Now, energy bands gaps in materials. So there are three types, as you can see: insulator, semiconductor and conductor. Insulator, where you can see the energy gap is very high, almost 6 electron volts. So it's very difficult that your electrons or the charge carriers to place into the conduction band, and then from the conduction band the charge carriers or electrons trying to jump into the valence band for recombination. So that procedure, it's not possible in the case of insulator. In conductor, there are bands are overlapping. The valence band and conduction bands are overlapping. That's why when you put a very small energy, then you can see current is rapidly increasing. That means both the bands are in overlap. Semiconductor is the flexible one, that where you can easily control the current. That means the band gap, it's in between the conductor and the insulator. So you can easily control for the germanium and the silicon semiconducting materials, you can control the flow of the charge carriers. Next, The silicon and germanium, these two are the semiconducting materials. So difference in conductivity, like insulator, that is 10 to the power minus 18 per ohm per meter. Semiconductors, that is in the range of 10 to the power minus 8 to 10 to the power minus 3 per ohm per meter. And conductors, you can see the difference, that is 10 to the power 18 per ohm per meter. So it's very, very high conductivity over there. So you can't control the current when you can increase the charge. Next, semiconductor materials. I have already mentioned the germanium and silicon. These two are the basic semiconductor materials, elementary material. So germanium was widely used in the early days of semiconductor development for transistors and diodes. Silicon is now used for the majority of rectifiers because silicon band gap is most suitable than the germanium, that is 1.1 electron volt almost, but in the germanium that is 0.7 electron volt. So that is very near to the conductor. So silicon is now, it's very popular compared to the germanium, and other compounds materials are very, very effective, under the part of semiconductor materials. So that widely used in the high speed devices that is requiring emissions or absorptions of light. Now, as you can see in silicon, that is the distribution is like 2, 8 and 4 because silicon atomic number is 14. So at the outermost shell, as you can see, the 4 electrons are there, number 1, number 2, number 3 and number 4. So 4 electron means it's a very neutral state, that is neither positive nor negative, because to stable the atom it requires 8 electrons at the outermost shell, but it has only 4 electrons. So for silicon, germanium, for the group 4 materials in the periodic table, that are all neutral. That means these are called semiconductive or intrinsic semiconductive materials or pure semiconductive materials, because at the outermost shell the electrons are 4, and to make stable the electrons it's required another 4 electrons at the outermost shell. Now band diagrams you can see the EV and EV is the valence band energy, EC is the conduction band energy, and in between this valence band and conduction band there is called the band gap. And this is bottom to top approach from valence band to conduction band, that is increasing the electron energy. But if you need to find out the voltage perspective, so definitely it's from conduction band to valence band, that is increasing voltage. These parts we will discuss into our next topics, but conduction band, valence band and the band gap, these three are the very important aspects of semiconductor under that is band diagram. Now intrinsic semiconductor, I have mentioned that suppose silicon is the intrinsic semiconductor because at the outermost shell there are 4 electrons, or it forms a lattice structure to share electrons. So these are called the covalent bonds, because silicon atom, this is suppose a one silicon atom with another silicon atoms, it's make the covalent bond because it can share their electrons, outermost shell electrons, and make it a stable state. Suppose for this electron, perspective of this electron, you can see that other 4 neighboring electrons can share their electrons. So this electron can say that it makes a stable state because that outermost shell it's consider 8 electrons. So in this way you can make covalent bond in this intrinsic semiconductor, and that is nothing but a crystal structure. Intrinsic silicon, definitely there is a compact crystal structure, but yes, we have to produce current further. We have to produce the free charge carriers. So if the valence band is full and no electrons are free to move about, then definitely you have to increase the temperature. When you increase the temperature, then definitely the charge carriers are energized, and these charge carriers are trying to shift to the conduction band. And if it's these charge carriers are able to shift to the conduction band, then these charge carriers are called free charge carriers. Free charge carriers. Okay, free charge carriers means when you can consider here that this is a free charge carrier that after break the covalent bond, then this free charge carriers are again trying to roaming around into the crystal structure to again place or recombine with the other charge carriers and make the covalent bond again. So there is a velocity, and according to that you can produce current, right? So this free charge carrier, suppose it's again trying to recombine with the valence band or opposite charge carrier and jump into this valence band over there. So semiconductor properties, that generation, the creation of an electron and hole pairing, recombination, that if an electron and the hole come in contact, they annihilate each other, and electrons and holes are called carriers. These are the we need to produce the free charge carriers so that these are roaming around into the crystals and release their energy. Therefore, semiconductors can conduct electricity, that when you increase the temperature, that means T greater than 0 Kelvin. 0 Kelvin means minus 273 degrees centigrade, but you have to increase it from 0 Kelvin, but not much current. That means at room temperature, it's around 300 Kelvin, that pure silicon has only one free electron per 3 trillion atoms. That is the survey. So covalent bond is the formation that when electrons are sharing their carriers with the neighboring atoms and make your covalent bond. So covalent bond can be formed between two atoms which have only one electron in an outer orbit or energy level. So covalent bond, when it's created, then you can create a compact crystal structure. But again, when we need to produce current, we have to break the covalent bond and release the charge carriers. See the scenario here, the silicon lattice structure. As you can see, in this way you can make the pairing or the covalent bonds of that silicon. So this is the center silicon over there, and according to that there are four neighboring atoms which sharing their electrons and make the covalent bonds. So shares with the four neighboring atoms, 8 electrons in outer shell. Then in this way you can make this total structure. At 0 Kelvin, all electrons are tightly shared with neighbors, no current flow. Now when we add heat, even to room temperature, allows some bonds to break and electrons can flow in this way. When there is a covalent bonds are break down, then electrons are again released, and when electrons are released, as you can see, there is a absence of electrons, that is called your opposite charge carrier, it's positive. So positive charge carriers are automatically produced here, so that are called holes. So free electrons and vacancy left by electron, overall charge silicon, so that is hole must be positive. Increasing conductivity, well, the conductivity of the semiconductor materials increases when the temperature increases. That is the best way that you can increase the conductivity. This is because the application of heat makes it possible for some electrons in the valence band to move to the conduction band, what I have mentioned already. And second, another way to increase the number of charge carriers is to add them in form of an external source, that is called doping. Doping means impurity. External or implant is the term given to process whereby one element is injected with atoms of another element in order to change its properties. So semiconductors are typically doped with elements such as the trivalent materials or the pentavalent materials. Trivalent means boron, aluminium. Pentavalent means arsenic, antimony, phosphorus. So that enhance their electrical properties. So about the doping, adding impurities to the silicon crystal lattice to increase the number of carriers. And when we are talking about the extrinsic semiconductive materials, not intrinsic. Intrinsic is pure, but extrinsic is by doping. A crystal can be altered so that it has a predominance of either electrons or holes. So that is either N-type semiconductor or P-type semiconductor. If it's N-type, means the donor impurities, that is the group 5 elements. So at the outermost shell, one electron is extra. If one electron is extra, that we consider the negative or the N-type, because electron is negative. And if it's the trivalent like boron, aluminium, gallium or indium, if we doped boron with silicon, then there is one deficit of electrons. If there is one deficit of electrons, then definitely that is a hole. So positive. So p type semiconductive materials. Donors, n-type material, that is the summary. As you can see, that add atoms with 5 valence band electrons, that is phosphorus, donates an extra electron that can freely travel around, leaves behind a positively charged nucleus. Overall, the crystal is still electrically neutral, and you can see the parameter, that is Nd, the donor concentration level, that is almost 10 to the power 15 to 10 to the power 20 per centimeter cube. Electron is free to move about the crystal, so mobility, that is 1350 centimeter square per volt. So here you can see when you doped phosphorus with silicon, sorry, then one electron is extra, and this free charge carriers or this electron can roaming into the crystal, so you can easily increase the conductivity. Now, extrinsic material donation of electrons, as you can see here, that if T is equals to 0 Kelvin, then all the electrons are lying in the valence band. But when you increase the temperature, it's not absolute temperature now, when you bring your materials into the normal temperature, then these electrons are trying to shift to the conduction band. Okay, and whenever the doping is the consideration, that is your n-type material, so one electron is extra, so definitely the donor level energy is very near to the conduction band, because conduction band, it's now n-type. After the reaction is takes place, after you add increase the temperature, then these electrons are trying to shift to the conduction band. So electrons are now in the conduction band, so that is n-type, and absence of electrons here, that is holes are generated in the valence band, so valence band is p-type. In this way you can create the p-n junction. So that is very near to the conduction band, and this is p-type semiconductive materials where boron is basically doped with silicon. Suppose that is an example. If boron, that means 3 valence band electrons, and accepts electron and provides extra hole to freely travel around, so leaves behind a negatively charged nucleus. Overall, the crystal is still electrically neutral, but called p-type silicon added positive carriers, that means acceptor concentration level, that is atoms per centimeter cube, and movement of the holes requires breaking of a bond, that is the mobility is very low compared to the electrons, that is almost 500 centimeter square per volt. So the p-type material means positive, so that is near to the valence band, the acceptor energy. The acceptor energy is very near to valence band. If a small displacement of the electrons towards the conduction band, then definitely here holes are created. So the increasing conductivity by doping, if we can see here, if the arsenic is doped with silicon, then arsenic is the group 5 elements, 1 electrons extra when it's after doping with the silicons, then this extra electrons are roaming into the crystal structure. Similarly, boron is doped with silicon 3, so holes are generated automatically, and these holes are also roaming around. So thank you for this first lecture of this semiconductor p-n junction and the digital electronics. In the next lecture, we will discuss about the depletion region and the p-n junction formation and the Fermi levels. So thank you everyone. See you into the next lecture.